Hello everybody, in this lecture we will be solving 2010 IMO problem number 2. Here is a view of this problem. Let I be the incenter of triangle ABC, and let me at the same time highlight those given points here. And let gamma be its circumcircle. So the circumcircle of triangle ABC, you can clearly see it here in this picture. Let the line AI intersect the circumcircle at the point D. Obviously D is the midpoint of minor arc BC because AI is an angle bisector. Okay, let E be a point on the minor arc BDC again, and let F be a point on the segment BC, but the condition for these 2 points is such that these angles BAF, which I clearly marked here, and the angle CAE here must be equal and such that it is less than the angle bisector, less than half of the angle A, less than A over 2 basically. Then we would like to show that when G is the midpoint of segment IF, you can see I and F, points F here, then we would like to prove that DG line, DG and EI intersect on the circumcircle. So I twisted this problem slightly and reformulated in the sense that I let EI intersect circle gamma at the point L, right? So EI extended, so I have it on this red color. Let's call that point as L. And once I identify EI extended intersection with the circumcircle as L, what I do is I connect the points D and L and let the intersection with IF, call it as G prime. Now recasting the problem such that I want to show G prime is in fact the midpoint of IF. When that's the case, so this is basically a type of phantom points argument. Obviously G prime would coincide with G, and the statement of the problem, the conclusion will follow, right? So we twisted the problem such that let me write those steps carefully again. So extend EI to meet gamma at L. Now connect D and L and let the intersection, let G prime be the intersection of IF and that point, that line segment DL. Now we would like to show that in fact FG prime is equal to G prime I, establishing that G prime is in fact the midpoint, implying as a result, that in fact G prime is nothing but identical to the point G given in this statement. Okay, so I will be using a computational approach. The main idea is to measure the line segments and eventually to give the final step using Menelaus theorem. And if you check AOPS discussion forums, you will also see a few solutions which use actually this approach as well. There's other approaches as well, but I kind of enjoyed this one, looking at different solutions. I forgot which solution that I picked, so this proof, the details, you can find it on that AOPS page. But having recasted this problem in this following sense, now let's start with a few things. First of all, a few housekeeping items maybe, because the incenter is involved and we are drawing the ray from A to the incenter I, meeting at the circumcircle at a point D. This reminds us of the incenter excenter lemma, where D is the center of the circumcircle of triangle BIC. So as a result, DB is equal to DI, which is also equal to DC. right? So we remember it. So by in-center, x-center lemma, let's write that down. dB is equal to di, which is equal to dc. In fact, if you let that circle intersect AI, ray AI at a second point beyond I, that would be M, and so therefore dm is also equal. And in fact, if you remember from our in-center x-center lemma construction, we know that bm is simply the external angle bisector. Now be careful, we already know bi is the internal angle bisector, and secondly, the claim is that, and you can easily prove it, these two angles are also equal, suggesting therefore that this is a 90-degree angle here. So angle angle IBM is equal to 90 degrees, and truly so, because as I said, D is the center of the circumcircle of triangle BIC, and that circle goes through the point M, and MI is the diameter of that circle basically. So what I would like to do next is to use some length measurements. In particular, I'm interested in measuring line segment AM. I claim that AM is simply equal to, knowing that ID now is equal to DM, AM is simply 2AD minus AI, obviously. I hope that's clear. Okay, so now let's establish some similarities. I need actually two sets of similar triangles. The first set will be based on this angle here. So we established this angle here is 90 degrees, and then there's another b over 2 here. So therefore angle ABM. So let's write that down. So let's have this for now. We'll make use of it in a minute. Secondly, let me write that down here. Angle ABM, I think it's clear, is equal to 90 degrees plus angle B over 2. But there's another angle which measures this, and that's exactly angle AIC. Angle AIC. And I hope this one is also clear, mainly because, well, obviously angle CAI is A over 2, right? And similarly ACI is C over 2. So therefore 180 minus A over 2 minus C over 2, obviously. So this angle here, let me write that down. So if I draw this new line here, so as a result, so let's write that down. Therefore, triangle ABM is similar to triangle ABM AIC. ABM, AIC, those are similar triangles, namely because they both have these angles 90 plus beta over 2. This one is also 90 plus beta over 2. In addition, this was an angle bisector, so this angle is A over 2. This corresponding angle is A over 2. So these two triangles are similar because of angle. But because that's the case, those triangles are similar, we have some very nice length relationship. The relationship that I'm interested in is AM over AC is simply equal to AB over AI. And let me put a note next to it. Now I can simply combine the first and the second result. So let's call this number 1, call this number 2, 1 and 2. And now replacing AM here with this expression we got in item 1, we find that 2AD minus AI all divided by AC equals AB over AI. And finally, if I do cross multiplication for this expression, I would get AI times AD and minus AI squared equals AB times AC. And recall that there is 2 ADAI, so I'm bringing one of them to the right hand side. So minus AD times AI. So that's crucial. So I'll call this the star relationship. Okay, good. So we did huge progress so far. Now let's go back to the picture. And I claim, so let's have a look at this picture again. Let's make it a little bit bigger. Let's have a closer look. And let me call this point intersection between line segment LD and AF as N. Let's call this as N here. I already labeled that point. I claim that A, so we have our point A, N, D, A and D, triangle A and D, and A, I, E. A and D and AIE are similar by angle, angle, angle. Let me quickly prove this. Obviously, these two angles, this one and this one, they are equivalent, congruent, because they both subtend minor arc AL. And secondly, because recall that AI is an angle bisector, these two angles, oh, we already marked that angle, obviously. Those two angles are equal, but then by definition, these two little angles are equal, suggesting that the angles in between them are also equal. So therefore, we have showed that these angles are equal, those two angles are equal. What's remaining is, as you can see, the remaining two angles, of course, are equal by 180 minus the other two angles. So we have, so let's write that down now. So we have another set of similar triangles now. Oh, view, I think it's under, yeah, so let's go back to the 100% view again. Oops, come on. All right, there you go. Okay, so therefore we have proven that A and D and AIE are similar. So let's write that down. Triangle A and D is similar to triangle AIE, but that would imply that, for example, AN to AD is equal to AI to AE. But then rearranging it, we get AN is simply equal to AI times AD, all divided by AE. Okay, so let's call this 3, I should say 3, because this one we decided to call it star. In a similar way, I would like to establish a relationship for AF. Once I have AN and AF, this will give me the desired NF. My goal is to find an expression for NF, so that will help me use Menelaus. So for AF, I need another set of similar triangles, and this time I claim that triangle ABF, that's slim triangle ABF, is similar to AEC. And the reason is very simple. If you connect these 2 points, let me use a different color. Obviously, this angle is angle B, ABF I'm using, and this one is also angle B, obviously. The reason being that both subtend minor arc AC. Secondly, they have this angle and this angle that they share. So by angle, 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 again, ABF, AEC are similar. Triangle ABF is similar to triangle AEC. But then that would imply AF to AB is simply equal to AC to AE. Organizing it again, I will get AF equals AB AC, AB times AC, all divided by AE, and I'll call it expression 4, and let me put it in a rectangle again. Now combining 3 and 4, so we can combine these two, 3 and 4 would imply that, so we know AN, I know AF, so therefore NF is the difference. NF, which is simply AF minus AN, is simply, you just substitute for AF and AN from expression 4 and 3, that would simply be equal to AB times AC over AE minus AI times AD over AE. That's an A, and that's it. So actually we have the common denominator, so let me actually make use of that. So let's put a minus sign here, and let's put the common denominator here, a e, and let this expression, let's also include this and f. So let this whole expression be, say, so let's do it like this. Sorry for that. Let's call it 5, expression 5. Now, final step, consider this. So we know that LD intersects IF at G prime. That's our phantom point, and we need to show that FG prime equals G prime I, namely G prime is the midpoint of IF. So if I would like to make use of Menelaus theorem on triangle AFI, with line NG prime D. So Menelaus on triangle AFI with line NG prime D. Obviously that would give me, if you start from the point I, for example, IG prime G prime F times Fn and A times AD over DI, right? I hope that's clear. So therefore, let me write all this down. By Menelaus theorem, we know that, by Menelaus on triangle AFI with line or transversal, which we can call transversal NG prime D, we get that, as I said, IG prime over G prime F. Let's remember again. So IG prime G prime over G prime F, Fn over NA, and AD over DI, right? So I'll just finish that. So times Fn over NA times AD over DI, and that's supposed to be equal to 1 because NG prime D is a straight line. But then this would imply, so the desired ratio we need is this one. IG prime over G prime F is simply equal to ID over AD times, flip it, and then times AN over Fn. Now we can start substituting stuff in. So let's be careful on this one. So I so far have multiple expressions. I have used, let's see ID. So I need an expression for ID, but ID is just AD minus AI. So let's write that down first. So ID is just AD minus AI, all divided by AD. Let's keep AD intact. And for AN, we can use this one, number 3 that I just found. So that would simply be AI times AD, all divided by AE. And Fn would be this one, the number 5 that we just got. So that's a long expression, so let's be careful. AB, AC minus AI, AD, all divided by AE. Now we can we realize a few things. AE's here in these expressions cancel out, the AD's will cancel out, and also look at this, our star expression. Notice this expression here, which is exactly the same with that one, so therefore we can also replace it with what we've got here. So therefore on the numerator we are left with AI times this expression, which is AD times AI minus AI squared, all divided by AB AC minus AI AD, but that's simply equal to AI AD minus, by star expression, minus AI squared. But that's really nice, because so we just got a 1 here. So so therefore this implies that, so looking at our expression, that immediately implies that, so this implies that IG prime is in fact equal to G prime F, suggesting that therefore G prime is midpoint of IF, and as such it is the case that and G prime has to be identical to G, and that is exactly what we needed to show. If you remember how we recast the original problem in this alternative formulation at the beginning of the problem, and that was exactly our goal, which we were able to get by measuring the corresponding appropriate line segments and applying finally Menelau's theorem. Hope you enjoyed this solution and looking forward to see you guys in our next lecture.